So our next speaker is Sang-Jin Sin, and we will hear about holography, topology, and the stability of a flat band. Please. Sang-Jin, we cannot hear you. Please unmute yourself.
Thank you for the invitation and a nice introduction. So my issue is the following. If you look at the Kagome lattice, band structure suggests many interesting possibilities. However, as you well are informed at the, I guess, in the title of your workshop, flat band is fine-tuned. Therefore, generically, it should not be observed unless it is protected by some fine-tuned process. But there are materials where flat band is observed in RFS data. For example, COS and OFSN data, and apart from the multi-layered graphene. And the two ways to explain this is one, you look for some region, symmetry or other fine-tuning process, why perturbation is extremely small, or why there is some symmetry. Even in this case, even in the case you succeed to find it, we still have to deal with the interaction effect. If flat band is there. So conventional method is not so proper, I have to say. So in this talk, I want to suggest that there is a correlation-induced topology which is at work, right? And I don't have time to present here, but similar mechanism is working for the stability of a fermion liquid in heavy fermion system, I believe. So if there is any question in this issue, please make a question. Now, to treat the strong correlation effect in the flat band, we wanted to use holography, which is supposed to take care of a very strong interaction effect. So here, we are living in the boundary of this ADS space, which is the surface of the cylinder here. And the inside is the ADS space. So we have fermions in the right-hand side. Okay, so we have fermions living on the boundary, and which is a real fermion, and the dual fermion is living inside. And the ADS boundary is our real world. And now you want to look at the system at the criticality, where, all the details of the crystal structure is gone. And the criticality is classified by dynamic exponent G and the theta. And there is a metric which is a dual to it, which is presented below. So the hope is that there is one-to-one correspondence between this critical point and the metric. And for the critical point, we can solve the Dirac equation in this metric without adding anything. For the different critical point, for example, there is 3 figures. The first one is for G equal 1, next one is G equal 2, and the third one is G equal 3. So at each criticality, we can calculate the spectral functions. And the result is just the following. So in order to create the flat band, we want to do something near this critical point. So what we want to do is we want to break some symmetry in this language. So what you do is you introduce some fermion bilinear. And if this fermion bilinear condense, then you can introduce a classical field B mu nu at the boundary. And then you extend it to the ADS space inside. And then you couple it to the fermion bilinear of this dual field. So this is similar. This is very similar to the so-called 4-point interaction in weakly interacting system. But this is the recipe for the strongly interacting system. So the amplitude of this condensation field B corresponds to some gap function, and this magnitude is the gap size introduced by the order, which is introduced by symmetry breaking. And then for simplest case, and for the simplest symmetry breaking, which is by scalar, the result is a 3-figure. The middle one is the quantum critical point, and the left one is some positive condensation, and the right is the negative condensation. And you see that there is some metal insulator phase transition going on. So what we want to do here is we want to look at the critical point and the nearby, okay? And the nearby point means that there are some symmetry broken phases. And according to which condensation or which fermion bilinear you condense, we can introduce various different kind of symmetry broken phase. And then the idea is that the one of that symmetry broken phase is the flat band, and which is one special case of the topological, I think the zero mode structure. So let me just briefly review what is the story of a topological insulator. Now, if you consider phi field, which is denoted by kink in the red curve here in the right-hand side, and if you couple direct fermion psi to this kink type soliton, then the solution of this fermion is the so-called Jackiw-Rebbi solution, and which is denoted here as like a blue curve here. So it is a zero mode localized at the in the center of the kink, and that change of the from plus to minus can be considered as kind of a change of a mass from left material to right material. And in this way, you can realize the kink soliton in terms of some condensed matter system. So at the if you make such a system at the boundary, you can have fermion zero mode localized to that boundary. So what we want to do is we want to repeat the same thing in this ADS system. So inside there is a ADS4 or ADS5. At the boundary, you have our real world. So by the same mathematics, you have some, for example, I already told you that the if we have a scalar coupling, then we have such a metal insulator phase transition, which is described by this zero mode. And if you repeat the same story by symmetry breaking, not by scalar phi, but by two tensor bxy, then as you see here, you see the the flat band plus other things. So if you, you can play many things here. If you introduce chemical potential, you can bend such a flat band a little bit. And also, depending on the power of Bxy, power means that the Z dependence, which Z is here ADS holographic directions coordinate. Depending on the power, we can, you can call it one as a source and the other one as a condensation. And this is the variety shown at G=2 class. So the game is extremely simple. And here what I have shown is how to create a flat band in this holographic setup. I don't have time to explain more, but this is exactly the same type of the topological insulator surface mode. But here, surface means actually bulk of the our real system, right? Because the surface of the ADS is our real world. So here you have a bulk zero mode or bulk flat band. But it has a topological character. And you can try to compare theory and experiment.
Sorry, Sang-Jin, 2 more minutes, okay?
All right, so I think I basically delivered all the basic idea, and you can find the correspondence for G=1 graphene. I'm stocked with the ABC structure, and for G=2, now you can compare it with the COSN RFS data. If you are looking at the gamma point, near the gamma point, it can be considered as, and depending on whether you are looking at the gamma point or M point, you can compare with the left-hand side or right-hand side of the bottom graph. So and you can also consider the competitions of a flat band with all other order. And I don't have time to present more, but this is my conclusion. Due to the presence of the ADS space for strongly correlated system, the strong interaction can introduce new topological zero mode of flat band, and which explains the stability of the flat band for some of the observed system. And I believe that the microscopic mechanism of this stabilizing flat band is the smartness to this system. But I don't have a figure here, but you see that even in the case that there is a hopping between different hexagons, the existence of the U or Coulomb interaction can localize them. So that is, I guess, my picture, a microscopic picture. Thank you very much.
Thank you, Sang-Jin. We have time for one quick question. Sergey?
Very quick, maybe. What you seem to tell us is that there is an emerging symmetry which protects flat bands in the presence of interactions. I guess this will work for any weak non-zero value of the interaction. Is that correct?
No, actually not.
Is there a critical
what
value?
I'm saying is that I'm not talking about the symmetry. Of course, there is some symmetry related to this. Yes, that is also true. But what I want to say here is that the new topological zero mode, which is a bulk mode of the real system, which is actually a surface mode of one higher dimensional system. And such a topological, mathematical topological structure can make the flat band stable. And this stability is coming from the
by stable you mean that it's protected, right? By stable you mean protected. By stable you probably mean protected.
Yes. Not yes, stably. Yeah, yes, it is. This is a interaction-induced stability. That is how I would describe. Thank you for the question.
Thank you.
Okay, thank you.